Oh, okay.
Sorry, you took it so
Putting it up right here, right? Yeah. This is where you're putting it up.
I want SI.
Really?
Let me do this.
Yeah. No, I did the same thing. No, just the last 54.
Really?
Six people left.
Try it here.
Oh, awesome. Thank you.
Oh, have you noticed? I don't pay attention to anything that happens that you said. Exactly. Huh?
Me?
Yeah, John.
John, Sean.
Yeah.
Yeah, there's like 7,000 people.
Is there? I don't get on Facebook though. That's why. See the way you can find me when I'm on there.
What? Who, Joe?
I don't have Facebook.
Oh, come on,
That explains
Joe.
it.
Just get one just for the fun.
I'm not a Facebook in like 2 years. I deleted it.
Is Stuart in it?
I don't really get on my Facebook.
Is Gary in it? Is Savannah in it?
If you know somebody who is sick, please feel free to take contact to them. There's 2 or 3 people who are coming down with the bug, I guess.
Actually, it's the only way to manage the school.
I'm not gonna play video games. It's so awkward. It's like I'm playing like Assassin's Creed or like something, and then he just walks in and he's like, oh, yeah, I just turn off the TV or put on like the game or whatnot, the NFL game, and I'm just like,
That's probably your
that's what I said.
Get me play.
Get her?
Her. You have a girl roommate.
No. Oh, it's not like her.
And like get in. Like,
Oh, get him. Yeah, get him.
Dude, like dragons are addicted to Dishonored.
Never actually
If
saw
they come in, we play on my
Is it
Xbox.
local multiplayer?
Huh?
Is it local multiplayer?
No, it's a single player.
Yeah, I can go to TV right before I came.
Final boss is
Yeah,
multiplayer. We did not mind. Just try dragon fight the others. It's like over.
Yeah.
Just got one choice.
Crossbars on the back. I have my feet zip tied to it.
Wow.
So it's right there. So I'm sitting on my futon. Yeah, I have Netflix on my
I saw my friend.
Actually works. Cool.
And he had a sticky note on Libra, and I was like, no, I'm taking that email password. No, I was at Libra all this weekend just chilling, but yeah, I don't live in Libra.
Did you eat a pizza?
Is it pizza?
What time? PM? Oh, no, I wasn't there that early.
Breakfast pizza.
That's happened in our house.
Pizza for breakfast or breakfast?
Here's a pretty cool website. It's called APOD. Astronomy picture of the day. I think it's apod.nasa.gov. Every day there's something else up here, which is really cool. Really neat stuff. This is, God bless. There's stuff going around. Anybody got any flu shots?
Yeah, because the flu shot works on last year's virus, but go ahead.
Yeah. Only a year behind. All right, so this one, for example, is a video. This is pretty neat. It's got a video of all of the view of the moon. We only see one face. When we get to chapter 8, we'll talk about why we only see one face on the moon, but that's pretty neat. Some kind of orbiter has taken this. So every day there's something else along with some kind of explanation about it and further links. And so going back, this is yesterday's. That's pretty cool. Along with an explanation of what it is that you're seeing. That's the Russian craft that just came back from the space station. It's a shot taken of it landing from probably an airplane or something. Some kind of maybe Venus going the moon, occulting Venus or something. Pretty cool, neat website. It's got a lot of neat pictures in it.
That's like going on a trip down the block in the Milky Way.
Oh, I have one I want to show you here. if it's on APOD. The hexagon. Have you seen the hexagon on the south pole of Saturn?
Oh, wait, which one is Saturn? That's one with the rings? No, it's Jupiter.
Yeah, that's the one with the rings.
Saturn.
Oh, oh wait, Jupiter, the big one.
Yeah.
Wow, I feel a little slow right now. Oh, you did aim it on me. I'll learn about it eventually.
Doesn't Jupiter?
No, I'm smarter than a
Jupiter does have rings, but they're not very visible. But look at that. It's a hexagon. Can you see that thing? In the clouds? Weird. So this is the south pole, I think, of Saturn, and it was spotted by the Cassini probe, which is an orbit around Saturn, and then Saturn moved so that the south pole was winter. In winter, its axis is tilted like the Earth's, and so the south pole went into winter, and so couldn't get any pictures of it. Came back out again recently, and so they sent Cassini around to take another look, and there it is. It's still there. Really weird stuff. I don't know what this is. That's really bizarre. But this was on APOD, that kind of stuff.
Does it have anything to do with the magnetic pole?
Saturn does have a magnetic field. It's not on the North Pole. It's not on Jupiter's poles as far as
Just the bottom? It's not
just the southern pole. Yeah. One of those things. Okay, and I think I've got the podium working here. I'm sorry for all that trouble we had last time. And it turned out to be really quick to fix, and so I'm sorry I didn't even try last time. I apologize for that. Okay, so turning to the homework that you turned in today. Trying to give you an overview of this. The first question having to do with the distinction between y versus x, and then something like h versus t. What's the big deal? What's under the discussion here? What's the point? Anybody want to try?
Show time is like a spatial dimension, I guess, so we can measure it.
Oh, really? Okay. It blinked out on me again. Hold on. Excuse me. Mr. Disharoon, I'm sorry. Say it again, please.
To show time is like a spatial dimension.
Looks like a spatial dimension, doesn't it? You might, in fact, if you're not careful, you might forget that there is an important distinction between time and space. So I have a plot, for example, y versus x, say an inverted parabola. And then I have another plot which is made by making a bunch of measurements of a body which is thrown up and then falling back down. So I make measurements of the height versus time. They look the same, don't they? And so what I've done here is to make a history of something that happened. It's a changing object. But I'm showing it all at once. And you remember what changed. What is change? Change is a process. Actualization of the potency, right? That which is potential as such. So I throw something up. As I start to throw it, it's actually here. It has potential to be up there. Later it will actually be up here. It has potential to be somewhere else. So it's a process of changing from one actuality to another and back again. But when I take a picture like this and I have a history of it, all represented at the same time, where's the potency in that? There is no potency. It's all been actualized in some sense. It's all there. But there's no parabola in this. There's no shape like that in here that corresponds to its motion. Right? So this is, in some sense, as actualized time. And so we've lost the essence of time, because time in that has a reflection of change. And if we actualize it, there is no change left. Nothing can change. That object is forever a parabola, just like 2 or 3 or a triangle. We've lost the essence of change. But we've still captured something that happened. We've quantified it in some way, and the mathematics of it by which we study quantity is now going to be for us a picture here. And so I could take go through the process of what if I had a tangent to that curve at some point. So I'm going to pick a value of x here, and I'm going to look at the curve which is tangent to the line, which is tangent to the curve at that value of x, and I want to look at the slope of that, and that's the point of the calculus, is calculating the slope. Okay, and now doing the same thing over here, it's still a shape, right? And so why not? It's a shape. So I'm going to apply the tools of shape and algebra and calculus to the same curve. So, but now I'm going to say the significance of the slope of that curve. The significance of the slope of the tangent to the position versus time curve is speed, or it's analogous to speed. It isn't speed properly speaking, but it's analogous to speed. Speed is how fast is this thing going from here to here? That's speed, the rate of change in place. Now I'm going to make an analogy then, using this mathematics to say the slope of the tangent to the curve, position versus time curve, is analogous to speed. It's not speed properly speaking. It's analogous to speed. But this opens up a tremendous mathematical toolbox, being able to do this. And this is what Descartes and his contemporaries did, which really flowers, takes root when Newton applies this to planetary motion and develops his laws of motion and gravity, law of gravity. Okay, now the important thing to recognize here is I have actually two curves in this plot. Both in this plot and this plot, I have two curves. One is the parabola, and the other one is the slope. So let's investigate that just a little bit. Let's start off with, say, I'm going to, well, let's, do the same one. It's the one that's in the textbook, so why not? So he actually starts off investigating y versus x, and then 2 pages later, he's doing h versus t, and showing how you do exactly the same thing, right? But he doesn't want you to stop and think that there's nothing to this. He wants that somehow it's all the same, and you don't need to think about what's happened here. He really does want you to think about they're not precisely the same. Okay, so let's go to this question. We have this shape, and I've forgotten the form of it, but it's something like this. I don't remember exactly, some shape. I don't remember exactly what the constants are in this, but it's something like this. So he's going to, that's a function, and it's simply a parabola. You could write it more generically as a plus cx squared, for example. Some constant plus some other constant is proportional to x squared. So now what we've got is an equation. So of these two things, the equation and a curve, this one is more obviously related to something physical, because I can find curved things. But the equation is yet another layer away from the physical, because it's a relation between numbers, which come from physical things, quantity. But look, even the form of it is not something that you would see in nature, anywhere. An equation, you don't see equations anywhere. Equations are entirely up here. Quantity, of course, is of physical things, and so we've made it has its roots in physical things, but we've made these abstractions, and now we have this equation here. So it's interesting that what we have here a correspondence between an equation and a curve, and that's the step of Descartes to make this realization that shapes can be expressed as equations and vice versa. Go back the other way. And so now we're left with, okay, I want to find the slope of this. And so we go through the process of finding the slope of the tangent to the curve here, and we'll go through the steps again here in just a minute. But the point is that now you are plotting. You note that the slope depends on where it touches the curve. So if I want to look at the slope to the tangent, the slope of the tangent crosses the curve at this point, and then I vary x. So the slope, of course, right at the maximum is 0. It's horizontal slope. The slope is increasing. And the farther out you go, the steeper it gets. And so the slope of this is is going to look like this. It's going to be a straight line, actually. The slope of the tangent, which is, of course, what the derivative is about, is trying to find the slope of the tangent. So I have another function, y prime of x, which is going to be 2cx, and we'll see why that is. And this recipe from going from one equation, one function, to another function is called the derivative in broad terms, right? But the derivative, of course, is the slope of the tangent to the curve. Okay, so what is a derivative then, mathematically, to a mathematician? We call this a function is a map. It maps number to number. It maps x to y, just a number. It's like a machine that has an input and an output. You put in a number, and let me call this f here. Some function. You put in a number, and you get out a number. The machine accepts numbers, takes numbers as output. Okay, what is a derivative in this language? It's another machine. But what does the derivative take as an input?
X number.
No, a derivative doesn't take a number. You're finding the slope of the tangent. Yeah, what was it? It's a function. The derivative takes a function as an input. So a derivative takes a function as input. And what does it spit out? Another function. Right. It spits out another function called the derivative function. It's the derivative. Its input is a function and its output is a function. That's also called operator. An operator takes a function, spits out a function. Function takes a number, spits out a number. An operator takes a function, the machine, takes that machine and gives you another machine. So you have a new machine, which will then is a function itself. It will process numbers, right? So you have one thing here. This is a function. This is a machine that takes in numbers as inputs, spits out numbers. I have a new machine over here because this machine, this function machine, the operator created from one machine, created a new machine that's going to spit numbers, take numbers and spit out numbers. Okay. So that's what the derivative is. It's an operator in that sense, and the same thing for integral. Antiderivative, as we'll discover, is also takes a function, creates a new function. And so going back to this plot that we had here, I have two equations, two functions, and two curves. We've also got this correspondence between algebraic forms and curves. And the derivative, which is finding the slope of the tangent, also produces another curve, but it also produces another equation, again, corresponding equation to curves, same sort of correspondence. So this is all what I want you to try to keep in your mind while you're doing this. Of course, what you're learning, of course, is this recipe, but I want you to keep in mind what's going on here when you're doing this stuff. Why does this have anything to do with physics? Right? That's what's going on. Okay, so keeping that in mind, then, we go through this process, and we'll go through this. So you have some function, and we'll start with the function in the homework, y is x. So, well, actually, let's do y of x squared first. And this is the one he does in the book. I want the tangent, the slope of the tangent to the curve at some value of x, but I'm actually going to approximate that by taking a straight line that intersects the curve twice at x and x plus delta x. Right, just as he does in the book. And that gives me 2 points where the straight line crosses, and that gives me 2 values of y and 2 values of x. And then I'm concerned with taking delta y over delta x, but I want to make delta x arbitrarily small. It's always going to cross at 2 places. We'll never cross only at one, which is the tangent. But the slope of this line, which crosses at 2 places, is going to get closer and closer to the slope of that line. as we move these 2 points together. And that's the idea of the derivative. Okay. So doing that then, delta y is y of x plus delta x minus y of x. It's the difference in y at 2 different values, 2 different places. The 2 points there where it crosses gives you 2 values of y and 2 values of x. And substituting in, this for some reason eluded everybody, I think, in the homework. He skips this step in the book. I just wanted to see this step. Expand the binomial. Oops. There we go. And the first term cancels here. And we're left then with delta y is 2x delta x plus delta x squared. I wanted to see that step here. I wanted to, and that was something for some reason people didn't think I wanted to see. When I said show all the steps, that was the step that was missing, and I wanted to see that one because you're going to do it in your homework. Right. Okay. Then if we divide to get the slope, the ratio of the rise over the run, we still have left over here a delta x that's going to be going to 0, and in the limit, this just becomes 2x. And so we have an algebraic means of finding the slope. If we can convert the curve to the slope, if we can convert the curve to an equation, then we can use algebra to find out what the new function is, the derivative function, and then we can map that back to another curve, which is a straight line. Okay, so actually the first one we're supposed to do was pretty trivial, and that's y of x is delta, y of x is just x. So this was the second one, right? That was C. And, okay, so, and the more complicated one is D, which is cube. So you have delta y for cube is x plus delta x cubed. You needed to expand out the, oops, that's negative there. Needed to expand out the cubic. And then we're going to subtract off the cubic. That always cancels. So we're always looking at the second term in this. It's always going to be this term that survives. The others are going to drop out because we're going to divide by delta x, and the higher order terms are all going to drop out because delta x will be going to 0. So 3x squared plus 3x delta x plus delta x squared. And if we take the limit, these terms are vanishing, and so the derivative of x cubed with respect to x is 3x squared. Okay, so then you could plot the work for today in 3 pairs of plots, and that's what's on the handout there. I'll show you 3 functions, y of x and its corresponding y prime. So the first one is just a linear function. Y of x is just a linear function. The corresponding y prime of x is a horizontal line. Then y prime of x is a quadratic. That's pretty sloppy. Y prime of x is quadratic. Corresponding curve is a horizontal, is a sloped line, 2x. And then finally the cubic y is x cubed, maps to a parabola here, y is 3x squared. Okay, so you see this correspondence between derivatives and functions and curves. There's all this stuff is in there together. Okay, questions about that point? We'll do E and 54 here in just a second. So questions up to that point, the A through D. So I want you to be able to do this. You might remember these derivatives, but I want you to derive them. So if I were to give you, suppose, and I think he discusses this in the book, y of x is x to the nth. How would you calculate the derivative of x to the nth, where n is some generic power?
Set it, make a limit
Yes, sir?
as delta x equals to 0.
Good.
And then take f of x plus delta x, or which would be x plus delta x to the n minus f of x, which is x to the n over delta x, and the limit at delta x approaches 0.
Right. Okay. So now you need to do this binomial expansion of x plus delta x raised to the nth power. But you're only interested in the first two terms. The very first term, which is x to the nth, will cancel the x to the nth. Then you're looking for the next term, which is proportional to delta x. And so you don't actually need to keep track of all the terms. You only need the first two terms. So it's x to the nth plus what? What's the next term in the binomial expansion for this function?
N x to the n minus 1 delta x.
There it is. And the next one is n times n minus 1 over 2 times x to the n minus 2 delta x squared and so forth. But you don't really need these higher order terms because there are higher powers of delta x. You're going to subtract x to the nth. And so when you subtract that, then the numerator here, the delta y, is going to be n times x to the n minus 1 delta x plus other terms that involve delta x squared. Now this notation here, script O delta x squared. That means terms of order delta x squared. Terms involving delta x squared and higher. So if delta x is small, these are all small terms. That's what is implied by this notation. That I've got stuff here that's going to be really small, and even if I divide by delta x, I'm still left with stuff that's going to be small. So then when I take the divide delta y by delta x, I have n x to the n minus 1, plus terms involving delta x and higher order powers, which are all going to vanish when delta x goes to 0. Okay, so that's how you can prove the general case of x to the nth. All right, so similar to that, you should be able to do something like 1 over x. Can you find the derivative of 1 over x? What is y prime? Not because you remember it, but because you can do it this way, right? So it's a little bit of a challenge because you've got the thing in the denominator now, no longer in the numerator, but you can still figure it out. You should be able to do it. Okay. So E is just taking the function, the sum of two functions. You generate a new function. If you know the derivatives of f and g, then you can find the derivative of the sum. In fact, it's just the sum of the derivatives. So adding the two functions, the derivative is the sum. It looks simple algebraically, but suppose you have, think of this in terms of curves. You take one curve and you add another curve, which means that at each value of x, you're adding the values, the heights of the two curves, and you're creating a third curve. The slope to the tangent, the slope of the tangent of that curve, which is the sum of the other two, is the sum of the two slopes. It's not so obvious if you draw it, but it's from the algebra, it's very simple. The one that's a little harder is taking the product. If I take the product of two functions, now take the product of two curves and the product of two algebraic functions, now how do I find the derivative? And the answer is the product. First, it's the derivative of f times g plus the f times the derivative of g. And all of these are functions of x here, right? I should be careful, maybe not be quite so abbreviated. Each of these are functions. So that's called the product rule. And the proof for that is given in the homework, number 54. So I'll let you study the details of that one. So you can combine these things. For example, x squared is x and x, right? How about that? So what if you had a function x squared? Consider x squared to be the product of x and x. So the derivative of x squared is going to be the derivative of x times that plus x times the derivative of this, applying the product rule. Kind of really simple product rule. And what is the derivative of x with respect to x? Is 1. So this is x plus x, so this is 2x. So same answer, right, as an example. Really simple example. Okay. Questions on that so far? On that homework? There should be questions. I think you should have some questions.
Are we allowed to use like H for delta X and all that? Or you
Sure.
want us to
Yeah,
keep-
just be clear what your symbols are. What they mean. The symbols we use, of course, are mere symbols. They have no intrinsic meaning of their own. I write that. And this, and this. What do those mean? Right? They have no intrinsic meaning. What's a sign? So those are signs, mere signs. But there are some signs that are not mere signs because they themselves have physical meaning. If I drop this book, it's going to fall, right? That's a sign that the earth is there. Right? Clear. You know the earth is there because if I let go of this book, it's going to fall. It's a clear sign of the presence of the earth someplace beneath. So that's a real sign in the sense that it has real intrinsic meaning that's connected to the physicality of the thing. It's like an octagon, a stop sign. It is a mere sign. You don't know it's supposed to mean stop here, you just go right through it. Right? But you see skin of a snake on the ground, that's a real sign. There was a snake here. Who knows how long it's been, but there was one. Right? So those are real signs as opposed to mere signs. Math involves mere signs, and so whenever you're using something, I'm going to call this H. You got to tell me what H means. Don't assume that I know what it means. And so, as I should always do in this as well. Questions? Okay. Let me ask you a question then. Let's talk about dimensionality. So, very often y and x are both distances, so we would say in that case y has dimensionality length and x has dimensionality of length, for example. So let's suppose that's true, that they're both length. So, sorry, let me start over again here. Suppose we're talking about length, and then we're just talking about a geometrical object, an arch or something. So what is the dimensionality of the derivative?
It's none. It's a number over a number. It's a length over length.
Yes, ma'am. It's the dimensionality of y divided by the dimensionality of x. It's a ratio of things which have dimensionality. So in this case, if they're both length, the derivative is itself dimensionless. A slope is dimensionless if we're talking about rise over run and both of them are distances. Right? Slope of 1 means you go forward a foot, you're going up a foot. 1-to-1 ratio. Suppose, though, that the height is measured in length, but the time, of course, is measured in time. And so what is this ratio? dH dt, which is also called h dot. Right? The dot refers to what? With respect to time. Yeah, for some reason this got started. I think Isaac did it first, and everybody's been doing it since. The dot refers specifically to time derivative and nothing else usually. Most physicists use it to denote. So a dot is like a prime, except it refers only to time derivatives. Yes, sir, Mr. Flanagan? What?
You teaching.
Oh, sorry. Yes, thank you. Come on, guys, don't let me just flounder out there.
Come on,
Try to help me out.
man.
All right. Okay, so what is the, so it's the derivative, it's the ratio again. The derivative, so it's the ratio of the dimensionality of h to t, right? So it's the length per time. So it's a speed. Right. Distance per time. So that's true for every derivative. If you don't know what f and g are, so you have f and g and you're looking at the derivative of f with respect to g, the dimensionality is simply the ratio of the dimensionalities of those things, whatever they are. If you don't know what they are, you don't know what it is. It's just the ratio of those, and that's it. Okay, unknown dimensionalities. All right, next step. Now we're getting into the study of kinematics here. So let's look at a position vector. Can I have a vector function of time? Can a vector be a function? Yeah, sure, right? Watch the fly, buzz around the room. It's changing its place. And let's suppose I set up a, oh, okay, let me just first write it. I should always do this. First, in the primary meaning, distance and direction. What if the position vector changes if either of those change, distance or direction change? Then the position vector changes. Give me an example of something where the distance remains the same but the direction changes. Give me a physical example where that might. Sorry? Merry-go-round. Yeah, excellent. Right. If the distance, the position vector from the center of the merry-go-round to the kid riding the horse, the distance is the same, but the direction is changing. It starts off east and is north, and now he's west, and it keeps changing. Okay, that's an example. So the position vector is changing, even though the distance is not changing. How about the other? Distance is changing, but the direction does not.
You're just walking in a straight line.
Yeah, walking in a straight line away from the origin. Right. And then any combination. In general, distance and direction can both change at the same time. So we have, in this, we would have to consider, if I want the derivative of this with respect to time, I'm going to need to know the derivative of this with respect to time and the derivative of that with respect to time. And so we'll get it, I'll write it down. It's obvious. It's not obvious. Dang it, it did it again. Excuse me. He switched ports, and that was supposed to solve this problem, but it's still doing it. Okay, so the velocity is the derivative of the position vector with respect to time. What could it mean, the derivative of a vector? We talked about the derivative of a function, and now we have the derivative of a vector. So before we had the derivative of a number. Now we've got the derivative of a vector.
We talk about the change, how the vector changes.
Right, right. R of t plus delta t minus r of t. That's delta r over delta t. And we want the limit as the time goes very small. So in other words, this is delta r over delta t. Again, take the limit as delta t goes very small. So now we have in the numerator a vector, which is the vector that connects the before and after. So here is r at t, and here is r at t plus delta t. Now, where would I draw delta r?
From the two ends, the head thing?
Yes, sir. Starting at which one? From one head to the other head. Which one is the from and which one's the to? From here to there. So the end point is there. So this is delta r. It forms a triangle. That's delta r, right? So now I've got vectors. I'm taking derivatives of vectors. But because we've done all this work before about how we're going to manage this, it's really not difficult. Except we still got to talk about how to take a derivative of a direction. That's a little funny. So we're going to come back to that question when we do polar coordinates. but it's going to be easier if I use Cartesian coordinates. So in Cartesian form, how do I write the position vector in Cartesian form? Volunteer from back row. Let's do it that way. How do I write the Cartesian form for a position vector in 3 dimensions? Mr. Kelly.
R sub x.
Okay.
Hat.
That's fine. I'll take that.
Okay. Plus r sub y.
I'm going to leave some room here in a second here just for this. Times x hat plus r sub y, y hat.
R sub t.
Right. Also known as x, y, and z, right? X hat, y hat, z hat. That's probably more common. Okay, now I left some space in there because I want to emphasize that some things depend on time, some things don't in this expression. What doesn't depend on time? We're choosing the x, y, and z. Ordinarily the hats, the direction vectors, are ordinarily fixed. We leave them fixed. We choose the, here's this corner of the room here is our origin, x hat, y hat, z hat. Doesn't change. They're that way forever. Okay, so we don't change that. Hold on, let's see, I want to, there we go. Whoa. I forgot to change the camera a little bit there. Okay, so x hat, y hat, z hat don't change. But what our functions of time are the coordinates, the Cartesian coordinates, call them x, y, and z to make it simple, or to kind of connect to the notation that I had before. R sub x is the component of r in the direction of x, right? R sub y, r sub z. All right, let's deal with that second notation. It's just a little bit easier. Okay, so the velocity vector is the derivative of the position vector with respect to time, and now I've got things here I've got products here. I've got sums and products. So the derivative of this whole thing, how am I going to do that? Combinations of sums and products.
Using the product rule.
Yeah, and the sum rule. The derivative of the sum is the sum of derivatives. So the x, y, and z components are independently handled in the product of x of t with x hat, but x hat doesn't change, so it doesn't have a derivative. I could be concerned with this, d by dt, the derivative of x of t, x hat, and if I'm concerned with the product rule, I would say this is going to be x dot of t times x hat plus x of t times the derivative of x hat with respect to time. But x hat doesn't change with time, so delta x hat is always 0. It doesn't change from one time to the other. This is 0. Vanishes. And so when I'm doing the Cartesian components, all I've got to do is take the derivatives of the components, and I can just not think about the possibility that the unit vectors are changing. They're not going to change in Cartesian components. Not going to be true when we do polar coordinates. The unit vectors are changing in time, and the thing gets a little bit more complicated. So the first time we do this, we're doing it the simple way. Cartesian components are really simple in that way. Derivatives are nice and easy. You just take the derivatives of the components. So what is the component of the velocity in the x direction? X dot. Yes, sir, Mr. Cohen. The velocity, the component of the velocity in the x direction is just the time derivative of the x component. It's really easy, right? That makes it simple. Not all of our coordinate systems are going to be so easy, but in this regard, Cartesian is easy. And we could do one more. Another derivative will be the acceleration vector, and again, it's just going to be the next derivative, x dot, y double dot, z double dot. Now remember, this represents a vector that could be, r could be changing either in magnitude or direction. Excuse me, length or direction. So when we take derivatives, r itself may be changing in distance, the length of it may change, or its distance, its direction may change, or it might be some combination of all those. And doing this with Cartesian components works it all out for you. You don't have to be so concerned about it. Okay, so what's the magnitude of the velocity? The magnitude of the velocity is called the speed. So that's a technical reference. We reserve that. Oops, we reserve that for. How did that? Oh, I did that. There we go. Okay. Sorry, there we go. This is called the velocity. The velocity is the derivative of the position with respect to time. And this is, of course, acceleration. The next is sometimes called jerk. The next derivative, the derivative of the acceleration, is sometimes called jerk. It's not very common to say that. Not everybody will understand what you mean. Okay, the magnitude of the velocity is called what? Yeah, speed. Okay, so let's look in Cartesian coordinates. Let's look at the speed computed from above. How do I compute the speed? I want to do this in black. There we go. How do I compute the speed? From the Cartesian components, right? Sum of the squares of the Cartesian components. Take the square root. Right? Magnitude of the velocity. So that's the speed. Speed is always non-negative. There's no negative speed, just like magnitudes are always not negative. You can't have a negative magnitude of a vector. It's always positive or zero. Okay. So far, questions? Let's consider then, here's an interesting question, one in your homework. Let's suppose I have a curve like this, y of x. I draw a parabola, but I don't want you to just be constrained to thinking parabolas, but I draw a parabola because I have to draw something. And tangent to that curve is drawn here, tangent to the curve that touches at x. Now I want to construct the unit vector. Which is along the tangent. How do I go about doing that? That's your first homework problem for Wednesday. I gotta think, what day is this? That's your first homework problem for Wednesday. Find t, and it will be a function of x because it will change. The unit vector that's along the tangent. Any thoughts about how to construct such a thing? Yeah, the slope is going to be helpful to know. The slope is going to be helpful to know. How would you construct the vector if you know the slope of the tangent?
Do you know what point is supposed to hit the line?
Yeah, you're given x, so that's where it touches the line. So I'll give you a hint. I'm not going to take all the fun away. I'm going to give you a hint. Let's do the same construction we did before. Let's draw a line which goes through the curve at 2 points. Like that. If I were a better artist. And I can't undo very easily, I don't think. I don't know. There might be an undo here.
Undo button up there.
Ah, bingo. Ah! Great. Good deal. Okay. Let me try it again. So, the line that goes through those 2 points, yeah, it's not much better. The line that goes through those 2 points, could I make a vector out of 2 points? Yeah. Let's compose this vector. So it's as delta x is getting small here, remember this is delta x here, x plus delta x, as delta x is getting small, that vector is kind of related to the unit vector, but it's not the same. It doesn't have unit length, does it? But if you know how to get the vector and you can find if you know a vector, divide by its magnitude to get the unit vector. So there's a hint. So in other words, t divided by the magnitude of t is the unit vector, right? Okay, so that's enough hints for that one. Okay, let's take another problem. Since we have 3 minutes, let's take another problem. Let's consider the merry-go-round problem. Let's consider somebody who's riding uniform circular motion. Called, in other words, UCM, uniform circular motion. So, what is circular about the motion?
Distance is the same from the radius and the origin.
Yeah.
Wherever you.
Right. The magnitude of r is unchanging. It's a constant. That's what circular means. Oops, circular. Circular. R doesn't change, it moves on a circle. What kinds of circular motion? Well, there's on the merry-go-round, but there are other circular motion too. How about a pendulum, which is hanging from, has a length of a rod. Mass on the end is going to do this. No longer circular motion. No longer uniform motion. It's moving on a circle. But what makes it uniform?
Pendulum stop.
Yeah, the pendulum stops.
No, it stopped.
Oh, the pendulum. You mean our pendulum? Yeah.
It finally stopped.
It's,
stopped.
that's the trouble with that thing.
Yeah, that's true, but it got some nice lights.
It does that. Okay. When it is swinging, though, it's swinging along a circular arc. Swinging here. But that's not called uniform circular motion. Anybody want to make a stab at what uniform circular motion would want to be? Ms. Shaven, you want to try? No?
Wait, what?
What is uniform? Describe what would be called uniform circular motion.
Can I just take a stab at what the other one is?
I'm going to let
Okay.
Hodges.
Mr. Hodges think.
Oh, it's constantly going at the same rate around the circle, and it doesn't, go back and forth.
It doesn't go back and forth, right? Yeah, it doesn't go back and forth. Pendulum goes back and forth. Uniform circular motion would be two different ways of expressing it. Speed is fixed. The speed around the outside is fixed, so that would be the speed is fixed, doesn't change. Or another way is to measure an angle here. How would that angle change in time? If the speed is fixed and the distance is fixed, how would the angle change with time?
D
d
theta over dt is consistent.
theta over dt is what? Yeah, so let's talk about uniform translation. Uniform translation, I measure a distance from here to here and then from here to here, and the thing is moving, and I find that the distance is a direct variation in time. That is, distance is just proportional to time. Right? That's uniform translation. Now let's talk about uniform rotation.
Hardly.
How would theta depend on time? So uniform linear translation x depends on time. It's just constant times time. How about uniform rotation? Uniform circular motion. How is theta going to depend on time?